With the introduction of the Gibbs energy, we've now completed our tour, if you will, of thermodynamic potentials. But I want to spend a little bit of time talking a little bit more about the role of Gibbs energy and the determination of spontaneity for a process. Now, we'll recall that the general criterion that we found for entropy was that the change of entropy for the universe, which I can write as the sum of components that come from the surroundings as well as the system, must be greater than or equal to 0. All right, now for the surroundings, we don't normally measure these directly, but let's see how we might be able to do that. All right, they might be defined as the incremental change in heat for the surroundings divided by the temperature. But remember that the heat that the surroundings get is just the negative that the heat is given up by the system. So this gives us a handle on how we might determine this. And now furthermore, I'm going to say that maybe we're doing this under constant pressure conditions, so we can relate the heat content for the system to the enthalpy change. So I might be able to write something like this, where that differential change in the surroundings, in entropy of the surroundings, would be equal to the differential change in the enthalpy of the system divided by temperature. So now, under these conditions of constant pressure, I could write something down for the differential of the entropy change in the universe and write it something like this, where I've got an expression for the entropy differential energy change for the surroundings entropy can be taken from this, so it's minus dH system over T plus the differential change in the system entropy, and that this is greater than 0. All right, but now if I rearrange this a little bit and multiply through by temperature, actually I don't have to rearrange it very much, but if I take these things and put them on this side of the equation, multiply through by temperature, I'll get 0 is greater than or equal to dH system minus T times d entropy system. And this is something that I can relate to the differential change in the Gibbs energy for the system. So this has been a long-winded way of getting to the point that the Gibbs energy for the system must change in a way that reduces it. Or in other words, the delta G system must ultimately be less than or equal to 0. So this is our criterion for change and for a spontaneous process. Now let's write down a few of what could contribute to this. For example, we could have a process in which the enthalpy change is greater than 0, and the entropy change, this is for the system, is less than 0. But in this case, this quantity, delta H minus T delta S, would definitely be greater than 0, which tells us that this would not represent a spontaneous process. Or another way of saying this is that it would not be spontaneous at any temperature that we could name in this case. I could also have the opposite condition for each of these, that enthalpy change is less than 0 and entropy change is greater than 0. And in this instance, I would have that delta H minus T delta S is always less than 0 at all temperatures. And so therefore, this would be a case in which it would be always spontaneous. The more interesting case, and the one that really we spend the most time doing, are when we have one of these conditions, that is to say, delta H is greater than 0, but so is delta S, or delta H is less than 0, and so is delta S. In these particular cases, we find that it's going to depend on the temperature in terms of whether or not the process that's indicated is spontaneous or not. So in this particular case, at low temperatures, we would find that delta H minus T delta S is mostly going to depend on delta H, because T is going to cause this second term to be very small. At high temperatures, on the other hand, high temperatures, this quantity is going to largely be driven by the second term, because as temperature gets larger, this second term will begin to be larger than the first term. So whenever we have this sort of arrangement, we need to look at the temperature to determine what is most likely to happen. Let me give you an example of this. Let's suppose that we have a temperature of 260 Kelvin. All right, and 260 Kelvin, I have a process where the delta H for that process is equal to 6.01 kilojoules per mole. And I have a delta S for that same process that is 22 joules per mole Kelvin. So what I want to do is determine whether or not this process that has this value of the enthalpy change and this value of the entropy change, whether or not this process would be spontaneous at this temperature. Well, the way I would determine that is to simply calculate the delta G at this temperature. So I would have 6.01 kilojoules. I'll turn that into joules, so it's 6,010 joules per mole, minus the temperature, 260 K, times 22.0 joules per mole Kelvin. Okay, so the kelvins will cancel, and I'll end up with everything in joules per mole. And when I do this calculation, I find that the answer I get is plus 290 joules per mole. So is that spontaneous or not? Well, this is delta G. The answer that I've gotten is clearly greater than 0, so this would be not spontaneous at this temperature. Now, I could have made this more obvious and said, this is the enthalpy of fusion for water, and this is the entropy of fusion for water. So what I'm asking really is, will water melt at this temperature? And I think we all know the answer is that water melts at the temperature of 273 Kelvin, not 260. So the fact that this came out to be not spontaneous is not a big surprise. Now, what we'll ultimately find as we go through this is that one of the very best uses for Gibbs energy as an indicator of spontaneity are chemical reactions. Because for chemical reactions, we have enough tabulated data on the molecules that are involved in those chemical reactions that we can use that to predict spontaneity with very good reliability. And of course, as chemists, that is one of our chief concerns, is we want to be able to predict whether or not a reaction goes toward products and forms products, or if it maybe goes in reverse to form more reactants. So we'll have more on that when we get to Module 6. But for now, this gives us at least a little bit of a feel for how Gibbs energy and spontaneity fit together.